This video is part of my free CCNA series, and it's the How to Think follow-up after the fundamentals video. Today we're doing single area OSPF configuration concepts, not commands, not a lab walkthrough. This is the configuration logic video. Because most people don't fail OSPF because they type the wrong commands, they fail because they don't understand what they're trying to accomplish. So we'll build a clear checklist mindset. Get OSPF running on the right interfaces, control where it forms neighbors using passive interface, inject the default route when your network needs one, and verify in layers so you know it actually works. By the end, you should be able to explain, here's what I'm enabling, why I'm enabling it, and exactly what proof I expect to see. So, section A, the big goal, what making OSPF work actually means. When people say I configured OSPF, what they really mean is routers discovered each other and formed neighbors where they should. Routers became adjacent where appropriate and synchronized their LSDB. Routers ran SPF and installed routes in the routing table. Traffic can now flow using these routes. So the goal is not OSPF is on. The goal is OSPF participates on the correct links, forms neighbor relationships only where intended, and exchanges topology with each other, and that produces correct routes. Everything we discussed today is in service of that. Now, section B. Here's a mental shift that makes OSPF configuration make sense. OSPF is enabled on interfaces. Yes, you turn on an OSPF process, but OSPF actually only works on interfaces that are participating. So the first question you should ask is, which interfaces participate in OSPF? Because interface participation controls which links send and receive OSPF hellos, which neighbors can even form, and which networks get advertised into OSPF. So conceptually, your first configuration goal is simple. Decide which interface should run OSPF and which should not. Now here's the practical mindset. In a typical single area design, you have two categories. Router-to-router links, which are transit links. These should participate in OSPF, because you want routers to form in neighbors and you want them to exchange routes. And then you have LAN interfaces toward end devices. These often still need to be advertised, so the rest of the network can reach them. But you usually don't want neighbor formation with random devices, and that leads directly into passive interface. Section C, passive interface, what it actually means. Let's define it by the problem it solves. If an interface participates in OSPF, it sends hellos. On a LAN interface facing PCs, printers, servers, use networks, sending hellos doesn't really help. So end devices don't run OSPF. And worse, if there's another router plugged into that LAN unexpectedly, your router might form a neighbor relationship that you don't intend. So you want two things at once. You want that LAN network to be known in OSPF, but you do not want it to form OSPF neighbors on that LAN. That's what passive interface gives you. When an interface is passive, the network connected to it can still be advertised into OSPF, but the router do not send hellos out of that interface, so it cannot form a neighbor on that interface. Think of it like this. Advertise the network, but don't try to talk OSPF on that wire. But where is passive commonly used? User-facing LANs, server LANs, and an interface where you only want to advertise reachability and not form neighbors. And where is it usually not used? Router-to-router links, because you need hellos and adjacency there. So the logic is simple. Transit links, not passive, they form neighbors. Stub LANs, passive, advertise network and no neighbors. Section D, default route injection, why it exists. Imagine multiple internal routers running OSPF, and somewhere at the edge you have one router that connects to the internet, a wide area network, a firewall, an ISP, and some outside network OSPF is not learning routes from directly. Inside OSPF, routers know about internal subnets, but what about everything else on the outside? If a router receives traffic destined for an unknown external network, it needs a rule. That rule is the default route, 0000/0. If you don't have any more specific route, send it this way. So, default route injection means that one router tells the rest of the OSPF domain, if you don't know where to send traffic, send it to me. That router is acting like an exit point. And default originate simply means that announce a default route into the OSPF. Once injected, other routes will have specific routes for internal networks and a default route for any unknown external destination. Here's the critical condition. You don't invent a default out of thin air. The edge router must already have a default route in its own routing table pointing toward the outside. Then it can advertise that default into OSPF, so internal routers learn it. So the mental model is edge routers know how to reach the outside via a default route. Edge router injects that default route into OSPF. Internal routers install the default route pointing to the edge router. Now, the verification mindset. People often check one thing like, I see a router, so it must be working. That's risky. A good verification mindset is layered, because OSPF builds results through layers. Think of verification like a stack. Neighbor layer, database layer, routing layer, and then default sanity layer. Let's walk each. Layer 1. Neighbors. First, verify neighbor relationships are on the link where you expect them. Because if neighbors aren't forming, nothing else matters. Conceptually ask, do I have neighbors on the transit links? Are they reaching the expected stable state for adjacency? And the big rule, no neighbors equals no OSPF exchange and no routes. Layer 2. LSDB. If neighbors exist, the next question is, did we synchronize the topology? Conceptually, you verify, do I see link state information that includes the networks and routers I expect in this area? Does it look consistent with the topology? You're checking for the map, not the directions yet, because you can have neighbors but still have an incomplete exchange. So layer 2 is, do we have the network map? Layer 3, routes. Now check the routing table. You should be able to say, I expect to see these internal networks learned via OSPF. I expect their next hops to point to the right direction. And I expect the default routes if we injected it. This is also where understanding cost matters, because if a route exists but takes a path you did not expect, that can be a metric expectation issue. Routes are the main output of OSPF, but they're not the first thing to check. They're layer 3. Layer 4. Default sanity. If your design includes default injection, conceptually, do internal routers have a default route learned via OSPF? Does it point to the correct edge router? And does the edge router actually have a working path to the outside? Because default injection without real upstream connectivity is useless. So the final proof is the inside routers know where to send everything else, and the edge router can actually forward that. Now let's make it concrete. Example 1. 3 routers, single area OSPF. Picture R1 in the middle, R2 on the left, and R3 on the right. R1 connects to R2 and R3 via transit links. Each router has a LAN with end devices. Conceptual configuration logic is that once you enable OSPF participation on the transit link so that R1 forms neighbors with R3 and R3, then you advertise the LAN network so everyone knows how to reach them. And then make LAN interfaces passive so you advertise them but do not form neighbors with PCs. After that, you need to verify in the layers. First, neighbors. R1 has 2 neighbors. And then LSDB. Everyone sees the same area topology. That's good. And then routes. R2 knows R3 LAN and vice versa. Example 2. Now you need to add internet access. R1 has a connection to an ISP or firewall upstream. Conceptually, R1 has a default route pointing upstream. R1 injects that default into OSPF. R2 and R3 learn a default route via OSPF pointing to R1. Now, any unknown destination goes toward R1. To verify, R2 and R3 have OSPF learned 0.0.0.0.0/0, and next hop is R1, and R1 actually can't forward to the ISP. Common mistakes that break this logic. 1. If I advertise a network, I automatically form neighbors on that interface. Not necessarily. You can advertise and still prevent neighbor formation using passive interface. 2. Making a translink link passive. If you make a router-to-router link passive, hello stop. No hellos means no neighbors, and no neighbors means no LSDB sync. 3. Expecting a default route to appear without injecting it. OSPF doesn't magically create a default. If you want it, the edge routers must have it and inject it. 4. Verifying only routes and ignoring neighbors/LSDB. Use the layered approach. Neighbors to LSDB to routes and to default. 5. Thinking OSPF enabled means every interface participates. No. Your job is to deliberately choose participation. Let's summarize the configuration logic into one clean checklist. To make single area OSPF work, you need to do 4 things. 1. Choose interface participation. Enable OSPF only on interfaces that should be part of the routing domain. 2. Control neighbor formation using passive interface. Use passive interface on LAN facing links to advertise the network without sending hellos. 3. Inject the default route when needed. If one router is the exit to the outside, it advertises a default route into OSPF, so internal routers know where to send unknown traffic. 4. Verify in layers. Neighbors. Are we talking where we should? LSDB. Do we share the map? Routes. Did SPF install the correct routes? And default. Do internal routers have a valid path to the outside? If you think in that order, OSPF configuration stops being a command memorization and becomes a logical system that you can easily reason about.